Jackie. My name is Savalan, and today I want to present my final course project to you, which is a replication of one of the papers that you gave us. I replicated the paper and I also added some models to it to make it better, maybe. And you can see the title of the paper over here, and it's about physical informed machine learning models and how we can use them to predict stream flow in future. Here you can see the outline of my presentation. First, I'm going to go over the problem statement, the introduction, then I'm going to talk about the literature, the related work. Then I'm going to present the methodology, implementation, and finally I'm going to talk about the results, the lessons that I learned, and the conclusion. As you know, in water management field and hydrology field, one of the most important things is to find out how much water we will have in future, because the stream flow, the surface water, is the most important source of water in our field, and we have to know how much water we will have in our rivers so we can plan and get organized to overcome any catastrophic event that we might face in future. To find out this stream flow, to predict this stream flow, different methodologies we can use, different models we can use. Two of the most important ones is the physical based and also machine learning based. Previously, traditionally, people try to use physical based, and in the past few years, machine learning models become famous, and people try, and scholars and my colleagues in water management field try to use it to solve this problem and get better accuracy. And both of them has their own pros and cons. Here I'm going to explain some of them. For example, the physical based models are rigid. They have rigid structure. You cannot implement them for different basins because they are based on rigid equations that cannot fit to different watersheds and basins in different countries. They also have parameters to calibrate, which is very time consuming and depends very high calculation power, hardware. And they also have very low prediction accuracy comparing to the machine learning models. But the important things and the advantage of them is that they give you information about the hydrological processes, the hydrological information, and hydrologically what's going on in that basin. It gives information about the physical equations in that basin, and because of that you can interpret them, understand what's going inside them, and get more knowledge and insight about the watershed or basin that you're working. On the other hand, as I mentioned, we have the machine learning based models. They also have their own pros and cons. Their disadvantages are that, most importantly, they try just to find a linkage between input and output. They do not care about if it's rational or not, if it's logical based on physical understanding or not. They just want to get to find out this linkage. And if we give them wrong information, they will give us wrong predictions, which means garbage in, garbage out. And they do not care about physical constraints or hydrological processes. But in comparing to the physical based models, they have higher predictive accuracy, which is very important and good. But having a high accuracy without no knowledge, or having a very good knowledge without low accuracy is not good, and we have to find out a way to having both of them at the same time. So some of the scholars and the my colleagues in water management field try to couple these two types of models to each other and build the physical informed machine learning models. And there are different ways to build them, and two of the most important ones are feeding the one of them is to feed the output of the physical based model to the machine learning model. The other one is to use a machine learning model with a loss function, which is constrained based on our physical understanding of the physical thing that's going to happen. Uh, but these two models have these type of models have also some problems. They do not care about the intermediate variable, and they do not predict them. So it's hard to interpret the model again. And also they are not flexible. They are very rigid because again they are they depend on these rigid equations. So we are going to talk about a new model that is proposed in this paper. But first, let's look at the literature. You can see here the literature and the previous works, and as you can see, most of them are about stream flow. I tried to write the hydrological related papers here, and because most of them are about stream flow, this is another proof that shows that stream flow prediction is very important. And also most of them use the second type of the of models that I mentioned in the previous slide. They use some loss function with a physical constraint. And here methodology. Because before I get into details for methodology, I want to give you overall information about that. To do this paper, to replicate this paper and to implement it, first I gather the data from the GitHub page that the authors gave me. Then the data, includes meteorological data like rainfall and potential evaporation, and also hydrological data like soil moisture, groundwater, and stream flow. After gathering them and doing pre-processing on them, I ran six machine learning models and also six hybrid models, and with different inputs. And finally, I compared their performance based on three metrics: NSE, RMSE, and p-bias. In this slide, I want to talk about the physical-based model that I used. I'm not going to get into equations because I didn't implement the physical-based model. It's model itself. I just used the structure of it as the authors used in the paper to couple it with the machine learning model. But this model, this model that they used, is one of the simplest models in water management. The name is ABCD, and they call it ABCD because it has only four parameters to calibrate, which is A, B, C, and D, and that's why it's very simple and that's very easy to implement, and it's very realistic. It's about the relationship of precipitation, soil moisture, groundwater, evaporation, and runoff. And it represents soil moisture and groundwater with two storages in it. And overall, it's very easy to implement and use. Here, I'm just going to show you the equations. I'm not going to talk about the details. This model gets the precipitation, potential evaporation, soil moisture. Then it calculates some state variables. And according to this model, the precipitation will divide in three parts to the three parts. One of them is the direct overflow that goes into the stream flows. One of them is evaporation, which goes up into the air, and the third part is soil moisture, which goes into soil. Also, some of this water goes down from the soil, the first layers of the soil, to the groundwater. We call it groundwater recharge. And also we have a storage, which we call the groundwater, and you can see the equation here to how to find the data for that. And some of this groundwater comes back up to the river, and we call it groundwater discharge. And the summation of this direct flow and groundwater discharge become the stream flow itself. I'm not going, and the author didn't use the equations. The only thing that's important is to use this structure. I'm going to use this structure and couple it with machine learning. Oh, and we also have two equations here, which are constraints to prevent model to act unrational. Because in hydrology, we believe that in a basin, the amount of water that comes in should be equal to the amount of water that goes out of this watershed. So these two equations try to be sure that this happens. And in this slide, you can see the name of the machine learning based models. I'm not going to get into the detail again. They are the normal common machine learning and deep learning models: LSTM, Gaussian process regression, super vector machine, the lasso rigid regression, and also CNNs. The authors in the paper didn't implement CNNs. I did it myself to compare with LSTM and see which one is better. And it's interesting that the outcome is different than what happened in the paper I'm going to talk about in the future slides. And the inputs are precipitation, temperature, and potential evaporation for these six machine learning models. And as uh, for our physical informed machine learning model, it has two steps. In We use the structure of the ABCD, and instead of the equations that you saw, we used the machine learning models, so we can make it more flexible, because this machine learning can find out these relationships in different basins, and it's not only one equation, and you can use different equations, because machine learning will come up with different equations and relationships between variables. It has two steps. In the first step, the model gets precipitation, so much of the previous time step, and potential evaporation, and predict the evaporation, the real evaporation. And then it uses the soil moisture and groundwater of this time step and previous time step, evaporation, the real evaporation that we calculated in the previous step, and also the precipitation to find out the stream flow. By doing this, we use this structure of physical understanding, the constraints of physical understanding, but also we use the flexibility of machine learning models. And here you can see the metrics that are used to compare the results. These first two, RMSE and percent bias, are common in all of the fields, I think. But Nash-Sutcliffe efficiency is one of the specific metrics that we use in uh, hydrology for simulation and prediction of different variables, especially stream flow. And the case study that I found the data for, which was in that GitHub page, is Anandapur Basin in India. The data was from 1980 2014, and the I divided the data to 20% for test and 80% for train. In the table, you can see the sources that the others gathered this data and gave it to us, and you can see the equation in the bottom of the page, the PET equation, which was used to calculate the uh, potential evaporation. Now for implementation, I use Python to implement the codes, and I used the codes on the GitHub that the others shared with us. I use Google Colab, Cross, TensorFlow, and Sklearn libraries. And for the machine learning, I use grid search to find out the best parameters. And for the deep learning, in an LSTM, did a trial and error to find out the best parameters. And as for the implementation steps, the code first get the data, pre-process it using the min max function to make the data standard. Then I compile the model, introduce the model, then the training and test. We have the training and test, and finally we evaluate the performance of these models. Here you can see some of the pictures. Here's the importing of the libraries. Here is the model itself, and here is the code for the metrics. And also, since I'm recording it and I have the chance to show you the implementation, I want to get out of the uh, PowerPoint for a minute and show you the implementations. Here you can see one of them, which is the machine learning LSTM, and I use different accounts to run them faster. So I use my wife's accounts and my mother's account, all of them. It's the those machine learning models for PIML implementation. And here also those machine learning models. Here you can see the LSTM that we coupled with the physical based model. And that's it for now. And sorry, for the results. In the result part, first I want to show you the parameters that the grid search and the trial and error that I used and I found for each of the models, for the PIML model and also the machine learning based models themselves. As you can see, when we use PIML or ML, the parameters will change for the first four models, which are machine learning, and for the deep learning ones, they are the same, and there's a little difference just in the units. Here you can see the results for machine learning based model. As you can see, the CNN has the best result, has the best performance. In the paper itself, they didn't use the CNN, so the LSTM had the best performance, but here the CNN, surpassed the LSTM. And as you can see in the picture, also it can better go on with the observation data. One of the problems in the hydrology is that we cannot get the peaks, but here you can see that the CNN could do it very good. Here you can see the PIML model results, and as you can see, the CNN again has the best results, has the best performance, either in predicting the evaporation or in predicting the stream flow. And comparing to the previous one, the machine learning based one, which CNN was 74 Naxat cliff or RMSE was 34. You can see here that the CNN NSE is 78 and the RMSE is 31. And also again in the graphs, you can see that it could get the peaks very good. And as for that water balance and that concept that we talked about, the water that go into basin should be equal to the water that comes out. The going in for all the models was the same, which was precipitation, but coming out is the evaporation and the stream flow. So the summation of them should be equal to the observation, and you can see in the last column the deviation, the percentage of deviation, which is about 3 to 8, which is very low and acceptable. And as for discussion and lessons that I learned how to implement these kind of models in practice, which is very important, I think, and very valuable. And I also find out that CNN has better performance compared to LSTM and the other models. And overall, deep learning models have better performance comparing to the machine learning models. These kind of models can capture the physical process of the basin. And as for the future steps, I think the most important thing is climate change right now in our field of study, and finding out what's going on in future is very important. So we can use these models to downscale the large scale data, which again is a very challenging thing in our field, and it has very errors. So we can reduce the errors, increase the accuracy by using them, or even in the future years, maybe by using these models in large scale climate change models, which are physical based right now, we can make them faster and more accurate. And also, we should, I think, find out which one of the structure of which one of the models, the complex or simple physical based models are better, and find out which structure is better to use. Either is it better to use a complex structure or a simple structure as ABCD model. And also, there's the problem of finding out which machine learning models are good, and we should find out a way to compare them in more detail and find out which machine learning models are best to couple with these physical based models. And also we should implement them in other basins, because different basins have different reaction and performance with different models, and we know it by experiment and by using different previous machine learning and physical based models. And finally, in this information in this paper, we find out that PIML models are the best models, and they do the prediction very good with higher accuracy, much higher accuracy comparing to the other ones. They can also be very flexible, because the machine learning methodology find out the relationship between variables, and they can give us very important insight about the basin and what's going on between different variables. And comparing the results, we understand that they are very the PML models are very sensitive to machine learning model that we use. So we should work more on it and study more about it to find out which models we should use. And finally, the authors of this paper, propose that we can use this kind of models in hydraulic structure and flood management and early warning. And right now, I'm working on droughts, and I want to implement these models for drought early warning, because one of the parts of my dissertation is about stream flow prediction, and based on that stream flow, finding out the hydrological drought in future. So I'm going to implement these to my dissertation and to my future study. And thank you very much. I hope you will like presentation.